Section 1.7, diagonal, triangular, and symmetric matrices. So there are lots of new terminology in this and definitions in this section, but all in all, it's a very easy section. So first we begin with the definition of a diagonal matrix. A diagonal matrix is a square matrix so that all the entries of the main diagonal are zeros. Such a matrix is called a diagonal matrix. Like, for example, if you look at these two examples, D1 and D2, on the main diagonal, I have 1, 3, and -2. Off the main diagonal, I have zeros. That makes D1 a diagonal matrix. The same is true for D2. Off the main diagonal, I have zeros. That makes this a diagonal matrix. So if you have a diagonal matrix, it doesn't mean that on the main diagonal, you have to have non-zero numbers. No, you can have zero, like here I have, on the main diagonal, I have a 0. That's okay. This is still a diagonal matrix. The definition requires the elements or the entries of the main diagonal to be zeros. So generally, if I have an n by n diagonal matrix, I can express it like this. Here, d1 to dn could be either 0 or non-zero. Yes, Adriana?
So an identity matrix is also a diagonal matrix?
That's right. An identity matrix is a diagonal matrix.
Okay, just want to be sure.
Yeah, that's it. Because off the main diagonal, and on the main diagonal, you have ones, and off the main diagonal, you have zeros. And since off the main diagonal, you have only zeros, that makes identity a diagonal matrix. Now, the good thing about diagonal matrices is that it's very easy to do algebra with them. First of all, it's very easy to find an inverse of a diagonal matrix. So a diagonal matrix is invertible only if and only if there is no zero on the main diagonal. Like, for example, between these two, D1 is invertible and D2 is not invertible because you have a 0 on the main diagonal. And finding the inverse of a diagonal matrix is very easy. You just need to find the inverses of the elements on the main diagonal. Like D1 inverse, as I've shown here, is going to be the inverse of 1, which is 1. And then in this position, the inverse of 3, which is 1/3, or the reciprocal of 3, which is 1/3. And finally, in this position, third row, third column, the inverse of -2, which is -1/2. Another example, if I have 5, 0, 0, 0, 2, 0, 0, 0, -7, then if this is my diagonal matrix, the inverse of this matrix, first of all, this is invertible because there is no zeros on the main diagonal. And what would be the inverse? 1/5, 0, 0, 0, 1/2, 0, and finally 0, 0, -1/7, and that's it. D2, however, this matrix here, this would be a singular matrix because there is one entry on the main diagonal that is 0, and it's impossible to find the inverse of 0. 0 as a real number is not invertible. The other thing about diagonal matrix is that raising diagonal matrices to the power is very easy. Like if I have this matrix here and I want to raise that to the power of 2, the only thing I need to do is raise each one of these numbers on the main diagonal to the power of 2. So I get 25 here, I get 4 here, and I get 49 here, and the rest of the entries are going to be zeros. So this D1 squared is going to be 1, 9, 4, and then the rest of them are going to be zeros. That would be D1 squared. Raised to the power of 3, same story. Just raise those entries on the main diagonal to the power of 3 or 4 or 5 or whatever power. Another special thing about diagonal matrices is that it's very easy to multiply diagonal matrices by other matrices on the left or on the right. So one can check that if you multiply a matrix A on the left by D, then you are multiplying each row of A by DI. So the first row will be multiplied by D1. The second row will be multiplied by D2. The third row will be multiplied by D3, and so on. Like here, if you multiply the matrix, this 2 by 3 matrix, by a diagonal matrix on the left, then you can easily check that. You're going to get D1, A11, then D1, A12, then D1, A13. So it's as if you just multiply the first row of A by D1, and then the second row by D2. So just by looking at this, you can do the multiplication. For example, if I have 2, 0, let's say 0, -3, I want to multiply that by a 2 by 3 matrix, 1, 2, -1, 5, 2, 8. Yes. Then if I know this rule, I know that it's as if I'm multiplying the first row by 2, so I get 2, 4, -2, and the second row by -3, so I get -15, -6, and -24. And if you're multiplying a diagonal matrix by another matrix on the right, if you put the diagonal matrix on the right, then the same thing happens, but with the columns. That is, this first column will be multiplied by D1, and this second column will be multiplied by D2. So the result is going to be D1A11, D1A21, D1A31. For the second column, it's the same as this one, except for it's times D2. Make sense? Any questions? Okay, next. We're going to talk about triangular matrices. There are two types of triangular matrices, upper triangular and lower triangular. What is a triangular matrix? A square matrix in which all the entries above the main diagonal are zeros is called a lower triangular matrix. And if the entries below the main diagonal are zeros, then it's called an upper triangular matrix. So if the numbers are below the main diagonal, then it's a lower triangular. If the numbers other than 0 are above the main diagonal, it's an upper triangular matrix. So that's another way of saying it. However, the condition is that if all the entries above the main diagonal are zeros, then it's lower triangular. And if all the entries below the main diagonal are zeros, then it's upper triangular. Notice that a matrix that is diagonal is both upper and lower triangular because it satisfies both conditions. If you have a matrix like this, which is diagonal, I can say all the entries above the main diagonal are zeros. So it's lower triangular. And all the entries below the main diagonal are also zeros. So it's upper triangular. Make sense? Next, we have this theorem about triangular matrices. Part A of the theorem says the transpose of a lower triangular matrix is an upper triangular matrix and vice versa. So it's very easy to check. So imagine you have this A11, 0, 0, A21, A22, 0, A31, A32, and A33. So imagine you have this matrix, which is a lower triangular matrix. I'm going to call that L. Now, what about L transpose? What happens if I just find the transpose of L. So the first row becomes the first column, A1100. Then the second row becomes the second column, A21, A22, and 0. And the last row becomes the last column, A32, A33. So as you can see, this matrix is upper triangular. So generally, I can say the transpose of a lower triangular matrix is upper triangular, and the transpose of an upper triangular matrix is lower triangular. Part B, you can check that the product of two lower triangulars is lower triangular, and the product of two upper triangulars is upper triangular. That is, if you have L1 times L2, the result is also lower triangular. If you have U1 times U2, the result will also be upper triangular. Part C, a triangular matrix is invertible if and only if the entries on the main diagonal are not zero. So this is similar to what we said about diagonal matrices. We said that if you have a diagonal matrix, then it is invertible if and only if the entries on the main diagonal are non-zeros. This is also true for triangular matrices. So a triangular matrix where all the entries on the main diagonal are non-zero numbers is invertible. So for example, think of this lower triangular, 1, 0, 0, let's say 2, 5, 0, 3, 0, 8. Yes. So this one is a lower triangular matrix because all the entries above the main diagonal are zeros. And I know it's invertible. How do I know? Because I look at the main diagonal. There is no zero on the main diagonal. So for that reason, I'm sure that this is invertible. Just by looking at that, I can tell. I don't need to do the inversion algorithm to see whether I hit a row of zeros or not. Just by looking at a triangular matrix, you can tell whether it's invertible or not. Same for so this is upper, same for lower triangular matrices. Part D, the inverse of a lower triangular matrix is lower triangular, and the inverse of an upper triangular matrix is upper triangular. So this matrix here, I can see it's upper triangular. Sorry, it's lower triangular because all the entries above the main diagonal are zero. And I can see it's also invertible because none of the entries on the main diagonal are zeros. If this is A, then A inverse would also be lower triangular. So the same things that I mentioned, you can also tell them in this way. You can say upper triangular transpose is lower triangular transpose is upper triangular. Product of lower is lower, product of upper is upper. Part C, there is no way I can show it like this, so same. But part D, inverse of a lower is lower, inverse of an upper is upper. You're good? I'm going to give you some time to find the inverse of this matrix here. And then you can check your answers. So let's say we have this upper triangular matrix, 1, 3, -1, 0, 2, 4, 0, 0, 5. And you can tell that this is invertible because none of the entries on the main diagonal are zeros. Okay, use the inversion algorithm, find the inverse of this matrix, and then you can check your answer here. I'm going to give you 5 minutes for that.
Sir, I had a question.
Yes?
So on On point C, it says that it's invertible if the diagonal entries are all zeros.
Non-zeros.
Oh, my bad. I misread that. Okay, thanks.
Okay. No problem.
Sir,
Yes.
how come you didn't change the entry 122 and divided by times it by 1/2?
The entry for which one?
822, because it's a 2 in the,
Okay, yeah, I have a two. This two?
yeah.
Okay, how come I did not change it here?
I guess.
Okay, so I'm just doing this added to this. Yes, so if I add this to this, I get 1, then I get 3, then I get 0 here. 1, 0, and then 1/5. If I add -4 times this to this, no change. -4 times this to this, no change. -4 times this, -4 added to this, 0. -4 times this to this, no change, no change. And -4 times this, oh, -4/5. Make sense?
Okay, because the way I went by it, I just multiplied the second and the third row with 1/2 and 1/5, so I could get my 1, 1, 1 in diagonal.
Yeah, you can do that. You can also do that. That's perfectly fine. So
Yes.
you can. This is something that I have to do next. Yes. So my next step would be to do 1/2 times row 2. That will give me 1, 3, 0, 1, 0, 1/5, 0, 1, 0, 0, 1/2. And here, if I divide this by 2, I get -2/5. Yes. 0, 0, 1, 0, 0, 1/5. And then my last step would be to do row 1 minus 3 row 2. That will give me identity here. Yes, and here I get 0, 0, 1/5, 0, 1/2, -2/5. And then if I do 3 times this added to this 1, 3 times this, 3 times this one. So am I doing it correctly? No, 3 times this. 3 times this added to this 3/2, -3. -3 times this, -3/2 added to this -3/2. And finally, -3 times this is 6/5. 6/5 added to 1/5 is 7/5. So this would be my inverse function. Make sense? So as we expected, this was invertible because none of the entries on the main diagonal is 0, and also it's an upper triangular matrix. So we knew that this is invertible, and we also found the inverse. Is that clear? Okay, let's move on. Next, we have the definition of a symmetric matrix. A matrix is symmetric if the original matrix and the transpose of it are the same. So if you have a matrix and you transpose it and it doesn't change, then it's symmetric. Like, for example, these two matrices here. I have 1, 4, 5, 4, -3, 0, 5, 0, 7. Now, if this is A and I transpose it, then the first row becomes the first column. I get 1, 4, 5. The second row becomes the second column. I get 4, -3, 0. And the last row becomes the last column. I get 5, 7, 0, 7. So you see, it didn't change. It's still the same matrix. So it's a situation where A transpose and A are the same. That would make this matrix symmetric. Now, if you notice, if I just draw a line here on the main diagonal, I can see that these two are the same. These two are also the same, and these two are also the same. Yes, that is Aij is the same as Aji. Entry on the ith row and jth column of A is the same as entry on the jth row and ith column. Like, for example, entry 1, 2 is the same as entry 2, 1. Entry 1, 3 is the same as entry 3, 1. Entry 2, 3 is the same as entry 3, 2. If a matrix has this property, then it is symmetric. So that's another way of defining a symmetric matrix. If you have a matrix, so that's for all I and j, entry on the ith row and jth column is the same as the entry on the jth row and ith column for any I and j, then that matrix is symmetric. Very good. So the two ways of defining a symmetric matrix. That's one way of it. And that's another way of defining a symmetric matrix. Okay. Next, we have a theorem about symmetric matrices. If A and B are symmetric matrices, that is, we know A transpose is equal A and B transpose is equal B. A and B are two matrices with these properties. And K is any scalar, so K is any real number. Then A transpose is also symmetric. Why A transpose is symmetric? Because A transpose is actually A. And of course, it's symmetric. A plus B and A minus B are also symmetric. It's very easy to prove because if I want to prove that this is symmetric, I need to show that A plus B transpose is A plus B. That is, I have to start here and end here. A plus B transpose. We had a theorem that A plus B transpose for any matrices is A transpose plus B transpose. Then, since A is invertible, since A is symmetric, A transpose is equal A, and B transpose is equal B. That ends the proof. It's a one-liner proof. And finally, for any matrix that is symmetric, any scalar times that matrix, like Ka, would also be symmetric, because Ka transpose is going to be K times A transpose, which is going to be Ka, because A is symmetric. So this step that I'm doing here, we had this in a theorem, the same as this one, which is true for any matrix. Any matrix, it doesn't have to be symmetric. For any matrix, we know that Ka transpose is K times A transpose. However, this step is because A is symmetric. Same as this one here. That's true because we know A and B are symmetric. However, the product of two symmetric matrices is not necessarily symmetric. So if you know that A is symmetric and B is also symmetric, it doesn't mean that AB is going to be necessarily symmetric. And here you have an example. This matrix here is symmetric. This one here is also symmetric. However, when you multiply them, you get this matrix, which is not symmetric. As you can see, A1, 2 is not the same as A2, 1. So I can say that the sum of symmetric matrices is symmetric. The difference of symmetric matrices is symmetric. Any scalar multiple of a symmetric matrix is also symmetric. However, the product of two symmetric matrices is not necessarily symmetric. Do we understand the theorem? Okay, next we have a theorem which adds the one condition, and if you have this condition, the product will also be symmetric. So the theorem says the product of two symmetric matrices A and B is symmetric if and only if AB is equal BA. So if A is symmetric, that is A is equal A transpose, and B is also symmetric, that is B is equal B transpose. And you also have this piece of information that AB is equal BA. So we know that generally this is not true for any matrices, for any two matrices. In general, AB is not equal BA. However, if you know that, if it's given, if it's a part of the assumption that AB is equal BA, then you can be sure that AB is also symmetric. Okay, do you understand the theorem? So we can say in general, A is equal A transpose and B is equal B transpose. These two do not imply that AB transpose is equal AB. So in general, for two symmetric matrices, the product is not necessarily symmetric. However, if you know that A is symmetric and B is also symmetric, and you also know that A and B commute, that is AB is equal BA, then that implies AB transpose is symmetric. AB is also symmetric, that is AB transpose is equal AB. Now the proof is also very easy. I want to prove this. I know that AB transpose is equal, this is the theorem we had in the previous sections, that for any two matrices, AB transpose is B transpose times A transpose. Now I know that I can use this and replace B transpose with B. I can use this to replace A transpose with A, and then I can use this to replace BA with AB. So I prove that AB transpose is equal AB, making AB symmetric. Are we good? Okay. Next theorem. If A is an invertible symmetric matrix, then A inverse is also symmetric. So if we know that A is symmetric, that is, we know A is equal A transpose, and we also know that A is invertible, that is, A inverse exists, then these two will tell us that A inverse is also symmetric. A inverse is symmetric. So I just need to prove that A inverse transpose is the same as A inverse, right? But I know A inverse transpose is A transpose inverse. So this was a theorem that we proved earlier. That is equal to, I can replace A transpose with A, and that's it. I have proved that the transpose of A inverse and A inverse are the same thing, making A inverse symmetric. Are we good? Next theorem. These are very easy proofs, just one-liner proofs, so these are actually good candidates for the tests. then we have this one. For any matrix A that is m by n, for any matrix that is m by n, A times A transpose and A transpose times A are symmetric. So what are we trying to prove here? We are trying to prove that A transpose is the same as A transpose. And also A transpose transpose A transpose is A transpose A. Because if I prove this, that means this matrix is symmetric. And if I prove this, that means this one is symmetric. Now, let's just prove the first one. A transpose transpose. We know that generally AB transpose is B transpose A transpose, right? So this one becomes A transpose transpose times A transpose. However, A transpose transpose is simply A. So this is A times A transpose. And I'm done. Is that clear? Okay. Last theorem. If A is invertible, so we know that A inverse exists, then A transpose and A transpose A are also invertible. So this is very easy because if A is invertible, then we know that A transpose is also invertible. If you remember, we said that if A is invertible, then A transpose is invertible and A transpose inverse is actually A inverse transpose. Yes. Then we also had this theorem that if A and B are both invertible, then the product AB is also invertible and the inverse of AB is going to be B inverse times A inverse. Yes. So if you just combine these two theorems, you get the proof for this one, because if A is invertible, then A transpose is also invertible. And you have the product of two invertible matrices, which is going to be invertible. So this is the proof. A is invertible. That means A transpose is invertible. And the product of two invertible matrices is invertible. So that will make A times A transpose or A transpose times A, both of them invertible. Okay, I'm done with this lecture.